Okay, yeah, thanks. Let's resume the class. Okay. So here, yeah, let's take a look at this case. So what's wrong? Okay. So first of all, there is nothing wrong about showing that P1 is true because one cat is still same color. The problem here is we are concluding that X and Y are of the same color based on this effect. So we are saying that X is of the same color as this group, and then when X is taken out, Y is coming back. We are saying that Y is of the same color as this group. So we conclude that X and Y are of the same color. But then, this is only true if there is some cats inside the group. So in the particular case when n is equal to 2, what will happen? So when n is equal to 2, then you start with, or when k plus 1 is equal to 2. So let's look at this case. Then we will have two cats. Exactly one cat will be X, and then the other cat will be Y. Is that okay? Now we take out X. So Y will be of the same color. We put Y back, we take X out. Oh, sorry. We put X back and take Y out. You just have X inside. Then X is of the same color. So far so good. Nothing is wrong because we have shown that P1 is true. So it is correct. But the problem here is that we cannot conclude that X and Y are of the same color. Because what? Because when Y and X are taken out, there is nothing inside. There is no common cat inside to make sure that X will be the same color as that cat, and that cat has the same color as Y. Is that okay? So the problem is the logic here. We are too lazy to assume that, okay, the general case happens. So we are too lazy to assume that, okay, we are always looking at the case where k is greater than 1. But k could be equal to 1. So when k is equal to 1, then you cannot make a conclusion. Is that okay? Okay, so this is something wrong here. Now, there are actually variants of the induction technique. So for instance, let's say we can have base case of 1 and 2, P1 and P2 to be correct. And then we show the inductive case like Pk implies Pk plus 2. So in that sense, we still can have Pn to be true for 1, 2, 3, 4, 5 up to infinity. The reason is that we have P1, and then we have this inductive case, so we know that 3 will be correct. And now we have P3, so we know that by using this inductive case again, then P5 is correct. So we have 1, 3, 5, 7, blah, blah, blah. This will all be correct. And then we start with 2, which is known to be correct. And then we will have what? We will have 4 to be correct. And then we will have 6 to be correct and 8 to be correct. Then in that case, we can still show that for any integer n, it is always correct. Is that okay? Okay? So let's do one example. Yeah, just a super simple example. This example says, okay, let's say this is the product of 3 consecutive integer. So if we multiply 3 consecutive integers, let's say positive integers, is, so the product will be divisible by 6. So we want to show this. So equivalently, we are showing this one. Equivalently, we are looking at a certain proposition, let's say Qn, which says n times n plus 1 times n plus 2 is divisible by 6. For every n is equal to 1, 2, 3, up to infinity. Is that okay? So we are trying to show Qn to be correct. Okay. How do we show? Okay. So let's try to use induction technique. Okay. So proof. So what should we do? Okay. What is the most convenient way to show this? How many base cases should I look at? And what is the inductive case that we should be looking for? So we can have 6 base cases, right? Or, yeah, let's do 6 base cases. So what is P1? So when n is equal to 1, then we are looking at 1 times 2 times 3, 6, divisible by 6. Okay? If we're looking at n is equal to 2, 2 times 3 times 4, it is equal to 24, divisible by 6. And then n is equal to 3, 3 times 4 times 5, it is equal to 60, divisible by 6. If you're looking at 4, 4 times 5 times 6, it is 120, let's say, divisible by 6. 5, 5 times 6 times 7, it is like 210, right? Divisible by 6. And then 6, 1, 2, 3, 4, 5, 6, 6, 6 times anything is divisible by 6. Is that okay? So we know that P1, P2, P3, let's don't be lazy. P4, P5, and P6 are all true. Okay? And then why do we want to have such a number of base cases? It is because we want to show the inductive case to be pk implies pk plus 6. Okay? So we assume that pk is correct. pk is true. Is true. Then pk plus 6 will be looking at k plus 6 times k plus 7 times k plus 8. Is that okay? Okay. So this will be equal to what? This will be equal to k times k plus 7 times k plus 8 plus 6 something. Is that okay? And then so I take out 6 here. So you will have 6 times. So we have k plus 7, k plus 8. But then we will have k and k plus 8 left here. Is that okay? Is that okay? So I also take out 6 here. So I make this into k plus 2. Is that okay? So I take out 6 of them. So I'll take out k times k plus 1 here. Is that okay? Does that make sense? So this is how we can write down k plus 6, k plus 7, k plus 6 into something like k times k plus 1 times k plus 2 plus 6 times something. Is that okay? Now, induction hypothesis, because we assume that pk is true, induction hypothesis says this is a multiple of 6. And this is also a multiple of 6. So in that sense, this whole thing will then be a multiple of 6. Is that okay? So here we are now showing that pk, if pk is true, then pk plus 6 will be true. So we have this 1, 2, 3, 4, 5, 6 as the base cases. Then we can show that for every n, this statement Qn will be true. If you are okay with this proof, could you please raise your hand? Okay, okay. So, but of course, for this one, you don't want to use induction proof. There is a much better proof. So how do we show that? 3 consecutive integers. If you multiply them together, it is a multiple of 6. So if you have 3 consecutive integers, right? It must contain a multiple of 3. So first of all, it is divisible by 3, right? And then if you have 3 consecutive integers, you must have an even number inside. So it is divisible by 2. If a number is divisible by 2 and divisible by 3, then it is divisible by 6. Is that okay? So here, okay, induction is nice, okay, but usually that could still be a much simpler or more intuitive proof that explains things. Okay? Okay. And there are other strange forms of induction. Let me show one more. Okay. So this example is not in the lecture notes, but then I've used that in the undergraduate discrete math course. But I like this example, so I want to show you. So consider this game. This is a solitaire game played by one person. So this game is like this. So we have some pebbles or some piece of chess, and then you assume that it is on an infinite board. So the board looks like a grid. So you must always place this chess on the grid point. Is that okay? So this game is like a cancellation game. So we can move. Okay, so what is the move that we can do? So whenever there are 2 adjacent pieces and there's one empty space, you can jump one piece over the other and take away the middle one. Okay, it is always 2 consecutive, and then one jumps over the other. So let's say we have these 4 pens. Okay. Let me try this. Oh, no, not good. Let me try this one. Okay, let me try these 4. Let's see if it works. Is it the table? No, the table. Simon, can you help me? How can we? Maybe not. Let's try. I'm going to do something bad. Okay. Yeah, remember to put this back. Okay, so we have 4 pieces here. So let me put it here. So I have 4 pieces here. Is that okay? So what we are going to do, hope you can see that. So we can do the jumping, so I can jump one over the other to an empty space and take this away. Okay? Now, only above, below, right, left. So I can jump this one to this one and take this away. And at this point, these 2 are too far away. We cannot jump one over the other, and the game stops. Is that okay? So, but then the target of this game is like you want to eliminate everything except one. Because each move you can take away 1 piece. You want to take away as many pieces as possible in the end. So for this case, if it is starting with a 2 by 2, what we can do is I can take this piece here, take this away, okay, and then I can jump this piece here and take this away, and then I have just 2 pieces here left, and they are adjacent, so I can jump 1 piece over the other and take this away. Is that okay? So in that case, I have just 1 piece left, and this is a good ending, a happy ending. Okay. Now, so how about the case when we have, okay, so when we have 2 by 2, we can eliminate everything except the last one. Okay. And then how about a larger example? Let's say we have 4 by 4, then what will happen? Let's try 4 by 4. Okay, let's try 4 by 4. Let's say we are going to jump this here. Imagine, I'm going to jump this here, and then jump this here, because it's now empty now. And then jump this back. Can you see that? So I'm going to start with something like an L shape. Focus on these 4 pieces. 4 pieces. What I'm going to do is I jump this here. So this is gone. When this is gone, then I have these 2 pieces. I can jump this piece over this place. Is that okay? And then this one is gone. This one is also gone. And then I have a piece here, I jump it back. Is that okay? The net effect will be, these three will be gone. If you are okay with the movement so far, could you please raise your hand? Okay? Yeah, or maybe I just write it more explicitly. So this one, I will jump this over so that this is becoming empty. This is going to become empty. So I have this one, and this one, and this one left. And then I'm going to jump this over to this empty location. So I'm going to have this one, this is empty, this is empty, and this is also empty. Is that okay? And after that, I jump this back. So I'll have this here, and this is becoming empty now. This is becoming empty now. This is becoming empty now. Okay? Is that okay? So the net effect is I'm actually deleting these three. Okay? Now, if I have 4 by 4, then what can I do? So I can use this L shape to delete these three. Is that okay? Now I have another L shape here. So I can delete these three. These three are gone. Okay? Then I have an L shape here. I can jump this here, and jump this back. So I can delete these three. Is that okay? And finally, I have an L shape here. I can jump this here, jump this here, and jump this back. I can also delete these three. Is that okay? Then what do I have? I have a 4 by 4 now. 2 by 2 now. Now, if I have a 2 by 2, then what can I do? I jump one over here, jump the other over here, and jump one over there. So I can get one left. Is that okay? So 4 by 4, I can do the elimination. Okay? How about 5 by 5? What should we do? 5 by 5. Let's try. Okay, let's try. So 5 by 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the last one, 1, 2, 3, 4, 5. Okay, 5 by 5. Then what can I do? I can use the same trick. I have an L shape here, right? I can delete these three. Okay, now these three are gone. They are gone. So I can look at this L shape, and then I'm going to delete these three. Does that make sense? Now, I have an L shape here. I can delete these three. Is that okay? Now, these three are gone. I have another L shape. I can delete these three. Is that okay? Here, I have an L shape here. I delete these three. Now, these three are gone. I have another L shape here. I can delete these three. Is that okay? And then I can delete these three. And then I finally can delete these three. So I can have one left. So what do we know? What do we know? We have a very strange thing. Okay, so 1 by 1 is okay. 2 by 2 is okay. Now 4 by 4 is okay. 4 by 4 is okay because of what? Because 2 by 2 is okay. Because I know 2 by 2 is okay, so 4 by 4 is also okay. Okay? Now 1 by 1 is okay, so it implies 5 by 5 is also okay. Okay, now how about 7? 7 by 7, what do you think? I'm intentionally skipping all the cases like a multiple of 3. Let's worry that later. But how about 7 by 7? So what we are going to do? 7 by 7, what will happen? 7 by 7 is like, let's see. 7, 1, 2, 3, 4, 5, 6, 7. Is that okay? And then here, 1, 2, 3, 4, 5, 6, 7. Da, da, da. So what we are going to do, we are going to cancel this, we are going to cancel this. Is that okay? If you can imagine, it's like, I don't know, do you play Mahjong? If you are playing Mahjong, it's like Mahjong pad. So Mahjong, you have this one, this one, this one, this one, right? So it's like an onion peeling. You're peeling the skin of the onion. So you have this one, and then you have this one, and then you have this one, okay, something like this. Is that okay? So after peeling off one layer, then what do we have left here? How many by how many? So originally 7, right? So I'm peeling this, and then I'm peeling this. So I will have 5 by 5 left. And because 5 by 5 is okay, so I know 7 by 7 is okay. So 7 is okay. And how about 8 by 8? 8 by 8 is like what? 8 by 8 is like, so I'm going to do this. This one peel, this one peel, this one peel, this one peel. So I'm going to peel 2 layers each. 2, 3, 4. So this one, I have 2 layers, 2 layers. I have 2 layers and 2 layers. Is that okay? I'm going to peel off 2 layers on the top, 2 layers on the bottom, 2 layers on the left, 2 layers on the right. So what will I get? If I start with 8 by 8, then I will get back to 4 by 4. Is that okay? And similarly, if you continue to do this, then if it is 10, then you peel off 1 layer. And if it is 11, you will peel off 2 layers on the top and at the bottom. So what is the pattern here? So what is the pattern here? So you can think of this as 1 and 2 are the basis case. You can think of this as, right? And in general, if it is a multiple of 3 plus 1, like this 4, then this will imply this is going to be a multiple of 3 plus 5. So this is 4 more than this one. Is that okay? And on the other hand, for this 5, it is a multiple of 3 plus 2. You will get into a 3k plus 4. It is just 7 and 5, the relationship is just 2 more. Is that okay? So here, 2 belongs to this case, so you get 2 more. 1 belongs to this case, you get 4 more. Is that okay? 4 belongs to this case, so you get 4 more. 5 belongs to this case, you get 2 more. Is that okay? Sometimes 2, sometimes 4. So this is, you add 4, you add 2, you add 4. And this one, you add 2, you add 4, and then you add 2. Something like this. This is a very interesting pattern, right? But then, what we are going to do, we are going to show that P1 is correct. So 1 by 1 is always eliminatable, let's call it. 2 by 2 is also okay. And then we show that if P 3k plus 1 is okay, then 3k plus 5 is also okay. The reason, you just peel off the top and then you peel off 3k plus 5. If 3k plus 1 is okay, then 3k plus 5 will be okay. For this one, you are going to peel off 2 layers. So you get back to 3k plus 1. And similarly, if 3k plus 2 is okay, then 3k plus 4 will be okay. Because for this case, you are going to peel off 1 layer. Is that okay? And then we are showing that P1 true, P2 true, inductive case 1 true, inductive case 2 true. Then we can show that therefore what? For every, so we will know that Pn is true for every n is equal to 1, 2, 4, 5, 7, 8, 10, 11, and so on and so forth. Actually, so Pn will be true for all positive integers that is not divisible by 3. Does that make sense? Does that make sense? So this is the idea. So induction, it does not have a specific form. Okay, as long as you can show some basis case and some inductive case, then the conclusion is what you need to consider based on the basis cases and the inductive cases that you can show. So this is what we can do. Okay. Now how about 3? How about 3? 3 by 3. So 3 by 3, impossible. Never. Okay. Now to show that 3 by 3 is impossible, then we need a difference proof technique. We will later show that. We will later show, maybe in the class or in the homework, that we are going to use proof by contradiction to show that 3 by 3 cannot be okay. Now, if 3 by 3 is not okay, actually, any multiple of 3 by multiple of 3 is not okay. Then this time is kind of induction. So 3 by 3 not okay implies 6 by 6 not okay. 6 by 6 not okay implies 9 by 9 not okay. Something like this. Or we can duplicate the proof. Okay? And one more. So we still have time. So I want to show you one more. This is perhaps the most interesting example of induction.